Cost-benefit analysis. How do you determine a program's value in monetary terms? How can you compare competing options such as to do or not to do, or to select Project A over Project B? Cost-benefit analysis offers one way to assess a project or program, making it easier to compare it to alternative options. The basic process is to first identify the alternative choices, such as to start a new clinic or to save the money. Second, list the benefits and costs over the life of the project, as we just did in the last example. Third, translate all the costs and benefits to monetary values as we showed. Fourth, since a decision is made today with the costs and benefits flowing over several years, we have to discount benefits and costs to obtain the present value. Calculating present value is part of the time value of money that is covered in a separate course module. A key part of this fourth step is selecting the discount rate. In our clinic example, we said the alternative to opening a new rural clinic is to save the money instead. If idle funds could be invested at, say, 7% compounded over 5 years, then we could use that rate as our discount rate for the alternative to saving, which is starting the new clinic. Alternatively, we could use the clinic's borrowing rate. If, for example, our primary lender would charge the clinic 8% to borrow money for 5 years, then we could use 8% as the discount rate, since it would be an alternative use of our resources. As this shows, the choice of a discount rate is determined by reasoned judgment. The fifth step is to compare the sum of the present value of benefits to the sum of the present value of costs. By doing so, we can determine if the project or program under study meets economic efficiency criteria. There are two measures. First, net present value is where benefits exceed costs, so a positive monetary result is economically efficient. The second economic efficiency test is the benefit-cost ratio, or benefits divided by costs. Economic efficiency is when the result is greater than 1. The last step is to make a recommendation. Using our example, it would be either saving the money or starting a new clinic. Now we can return to the clinic example to see how it might look when doing cost-benefit analysis. The monetary units shown here are hypothetical values for the stream of costs and benefits over a 5-year time horizon. The year column is column A. Costs are shown in column B. The initial cost of $150 is for construction of the new clinic, with $80 by the end of the second year for the remaining construction and equipment costs. For the other years, the $75 represents recurring costs. For benefit column C, the step up represents an increase in the target population learning about and using the new clinic, and then it stabilizes. Column D refers to the present value calculations. As we stated in the prior slide on the basic process of cost-benefit analysis, we have to put all of these monetary units into a present value, since the decision is made now to either save the money or start work on a new clinic. We could either save the money and earn 7% compounded annually over 5 years, or we could invest in the new clinic. We can then use that 7% as the discount rate in our present value calculations. In column D, we show the present value interest factor for one monetary unit, abbreviated as PVIF. The formula is shown in the sidebar. Just as a reminder, this formula comes from the other class module on the time value of money. The basic formula is the future value of $1 divided by the product of 1 plus the discount rate, all raised to the power of the year in which that cash flow occurs. The values in column D show that there's more power for early money than later money. Later money is discounted more because it has less opportunity value. Column E is the product of multiplying costs times the present value interest factor. That means multiplying column B times column D. The results reveal that the 150 of costs now, year 0, need not be discounted since they go out now. The 462 sum of column E represents the sum of the present value of all costs. Column F is the product of multiplying benefits times the present value interest factor. That means multiplying column C times column D. Again, the results show that the 50 of costs in year 0 need not be discounted. The 432 sum of column F represents the sum of the present value of all benefits. All of those steps lead to the bottom line assessment. Does this project meet economic efficiency? As we define the two measures of economic efficiency on the prior slide, we see that at a 7% discount rate, this project fails both tests of economic efficiency. The net present value is a negative number, and the benefit-cost ratio is less than 1. These results would suggest that the alternative of saving the money and investing the money at 7% offers some advantages. But remember that many of the items listed as benefits and costs are not actually directly attributed to the clinic system. Instead, they refer to costs and benefits of the clients. Conceptually, then, the 7% refers not only to the savings by the clinic system, but the opportunity values of those clients to use their time and resources differently. Perhaps the 7% rate is not the right rate. Sensitivity analysis means to use different percent rates to see what rate produces economic efficiency. In this example, no rate level will change the project's inefficiency. The only solution that works would be to reduce the first year's costs. We might just disregard this formal cost-benefit analysis and decide to go forward with the project anyhow. There could be a number of reasons to start the new project. It could be politics, the availability of donor money, or to advance the mission of our organization. In summary, cost-benefit analysis offers a systematic way to assess the value of projects or programs. In the end, however, a manager has to make a decision among hard competing choices that are more like comparing apples to oranges. They're very different.